and thank you for the invitation. So what I want to talk about, is a topic I've recently worked on with Hans-Christian von Bothmer in Hamburg, and also then afterwards Lukas Buhr joined. So he is a PhD student of Manfred Lehn in Mainz. Right, so this is so the initial motivation for what we are looking at is this. So though I won't say that much about it in the sequel. So we're interested in whether, well, smooth cubic threefolds or very general smooth cubic threefolds are stably rational or retract rational or not. So we were initially interested in this rationality problem, which is still open. So if we have X a smooth cubic threefold, we can ask, is X stably rational? Which means is the product of a projective space with X rational. We also ask, is X retract rational? Maybe I won't make that explicit. That's a notion due to Saltman. It basically means that X is a birational retract of a projective space. That's weaker than being stably rational. Or we could also ask the same questions, at least for very general X. Only for very general X. So it's known that such an X is not rational. That's a result by Clements and Griffiths using the intermediate Jacobian, but it's still open in this weakened form whether such an X is stably rational. So, for example, it could be conceivably be the case that there is some vector bundle, some strange vector bundle over every smooth cubic threefold, which turns out to be rational. So then you can try to study this question using results and methods due to Voisin. So there's this degeneration technique, but so quite generally, so what she proved, and also Collier-Tillane and Perutka afterwards in a more conceptual framework, is that if X is stably rational, or more, even weaker, just retract rational, then X is Chow zero universally trivial. So this is not a notion I'll use in the sequel, but I'll give you the background why we got interested in the type of question that I'll talk about. So X is Chow zero universally trivial. That means that the degree homomorphism from the Chow zero of X to Z is an isomorphism universally. So even if you base change to overfields of the field that X is defined over, which for me always will be C, the degree homomorphism is an isomorph Z. And then Voisin shows that this in turn is equivalent to a certain cohomology class on the intermediate Jacobian of such an X to be being algebraic. So this is equivalent to the class theta to the fourth divided by 4 factorial being algebraic. So this is a class on, so I'll explain the notation in a second. So this J of X is the intermediate Jacobian of X. So it's a principally polarized abelian variety. It's, if you want, it's Hodge H12X modded out by the image of the H3XZ, so the integral third cohomology. This theta is the class of the principal polarization of the theta divisor on this. So more concretely, you can think of this principally polarized abelian variety in this case as a Prim variety. So J of X is what is called a Prim variety. In this case, associated to some double cover of curves. So that's classical. So that's by results due to Mumford. So here, what you can do is you just pick a general line on your smooth cubic threefolds and you project from that line. And if you blow up the line, then you have realized that X has a conic bundle over P2 with a smooth quintic curve as discriminant. And you will also get a canonical double cover of this smooth quintic if you look at the lines and the fibers of this conic bundle. So this is, in this general situation, this is an entire double cover. So this is a plane quintic. So can be realized as a plane quintic. So this is genus 6, and this then has genus whatever 2G minus 1. So this is 11. Yeah, and there's this covering involution here, sigma acting on this curve. And then to this setup, you can associate a Prim variety, a so-called Prim variety, which turns out to be isomorphic to this intermediate Jacobian. So what is this Prim variety? So one way to think about it is just you just consider the norm map associated to this double cover. So just the push forward of devices from the pick. So this is 2G minus 2 to pick 2G minus 2 of D, right? And so you take this norm map, you take the line bundles in the pre-image under the norm map of the canonical on D that have an even dimensional space of sections, global sections, and that is your Prim. And the polarizing divisor, this theta divisor, can be chosen to consist of those line bundles with sections. But you could also kind of think of it maybe more easily, more simply as it's a slightly different realization as the points in the Jacobian of D tilde that are in the image of this anti-symmetrization map, if you want to. So where the Prim I talked about just a second ago would be a principal homogeneous space under this Primian. I think this is sometimes called the Primian. I don't know, but that's general background from Prim curves, which I don't really want to go into too much. The point is there is a Prim curve. We have a Prim curve on this Primian, and its class is twice the class of the class I wrote down up here. So this has class twice theta to the fourth divided by 4 factorial. So some other question becomes, we have this class here. So the question we're interested in, we have this cohomology class, which is a minimal cohomology class on this torus. So it can't be divided in the integer cohomology of this torus. And 2 times the class is realizable by an algebraic cycle. And we're interested in whether the class itself can be realized or represented by an algebraic cycle, not effective. So, no, that is not possible to do that with an effective cycle. But so to settle, so basically the question whether this class is algebraic or not is a question about the existence of certain curves on the Prim. So the question if whether theta to the fourth divided by 4 factorial is algebraic, it's the class of an algebraic cycle, reduces to, say, a question about existence of certain curves on this Prim. And we can try to study this question by degenerating the Prim. Yeah, so we can study this question by degenerating the Prim. And the curves along with it. So the curves will then degenerate to certain curves on the central degenerate fiber, certain special curves, so which we call prelog curves, or curves with additional structure, and their existence may be easier to investigate than the existence of curves of odd degree with respect to the natural polarization given by this theta divisor on the initial Prim. So I mean, so in a nutshell, what I want to say is our goal is we want to produce interesting degeneration Prim of these Prim varieties. Want to produce interesting degenerations of these Prim varieties. Interesting and degenerations that also subsequently make explicit calculations possible. So we want to write down these degenerations explicitly. So we would also like to degenerate these Prims into many components that somehow intersect in an interesting way, so that the combinatorial structure of the central fiber is more interesting as well than just the original. So these will be rather drastic degenerations that we want to look at. Okay, so that's the overture if you want to. And now I want to talk about skew matrices of linear forms on P4. Wait, I should also say, so what I'm going to say builds, so the approach builds on work of Druel and Beauville, Komarsky, and Sogaya, Komarsky, and others. Okay, so what I want to do first now, I look at the space of skew matrices of linear forms on P4 with its natural SL6 action. So I start with S, so I call this S. This is the projective space of skew matrices of linear forms here on P4, 6x6 skew. These are 6x6 skew matrices of linear forms on P4 with its natural SL6 action. Now you can take a skew matrix and just send it to SAS transpose as an SL6. So this natural action. And well, all right, so then so we're given this, and then we can talk about we can talk about the loci of, so these standard GIT loci of semi-stable, stable, and polystable points with respect to that action in S. Talk about S, upper S, so these are the stable points, semi-stable, points, and so semi-stable points for which there's a non-trivial G invariant polynomial non-vanishing on that point, and stable points. These are points in that have closed orbit, closed G orbit in the semi-stable locus and finite stable. So closed orbit with finite stabilizer, and then we also have the polystable points. Yeah, so those that have that are semi-stable and have closed orbit in the semi-stable locus. And okay, so that is this standard setup. And so then I want to consider the this GIT quotient. We have this GIT quotient, which I call M, which is so this the good, so categorical projective quotient for this action. Right, so I shouldn't, I don't know what it means to be a good quotient. I mean, well, lots of things need to be satisfied. So this pi, this is a morphism which is constant on G orbits, it's surjective and pullback, it uses an isomorphism of the sheaf of regular functions here on M with the G invariant regular functions on this space upstairs here is S, and lots of other things. So if you have an invariant G invariant closed subset in here in this SS, and I apply pi to it, I will end up with a subset of M, and right, so and 2 points here in this SSS map to the same point down here if the orbit closures meet in SSS. So have G invariant closed subsets that don't meet, then most of the images will be destroyed downstairs. All right, so I can identify the points of M with orbits of polystable matrices. So at least closed points of M get identified with orbits of polystable matrices. Right, and now, so what I want to talk about in the sequel, I want to talk about some birational modification of this M that is related to the intermediate Jacobian of a general cubic threefold, any cubic threefold actually. And for that I need some preparations. So let me say Gaia Kumarski. So this builds on work done by her, Gaia Kumarski, roughly classified, she roughly classified unstable, so non-semi-stable matrices and non-stable matrices under this action according to Skew formats, or she can classify them maybe into Skew formats. That's the right thing to say. So, but I mean that she showed that if, for example, a matrix is unstable, then it's in the same G orbit under this action as a matrix which has a certain pattern of zeros, 0 entries. So it has a certain specified pattern of 0 entries and certain positions, and that's exactly what instability amounts to, being unstable. But being non-stable is also equivalent to having being in the same G orbit as matrices of a certain format. So, and what we did then is we classified. So we classified in a finer way the matrices, or the points here in this projective space, with Pfaffian matrices in the semi-stable locus with vanishing Pfaffian, and yeah, so we classified these more precisely, so maybe let me let me phrase that as a theorem, and I'll show you the list in a second. So what we show is that if we have a matrix, of this type, semi-stable and with Pfaffian 0, then up to the G action, M is one of 6 types. And so let me
Sorry, Christian, may I ask a question?
Yeah, please.
So this good quotient is it the Chevalier morphism roughly, or are you taking characteristic polynomials? Is that what the what the GAT quotient classifies?
I don't know. It's just the abstract GAT quotient. I have no. I don't. So what is the?
Maybe
yes.
I can ask differently. So these unstable guys, do they correspond to some particular orbits? Like, do you have a regularity? A regularity condition on the orbit that ensure that it is stable. I mean, regular orbits will be closed, and so they are going to. No, sorry, semi-stable orbits are closed. So if they have the right dimension, they will be stable. Is this correct, or?
Well, the semi-stable orbits that are, whether the orbits of semi-stable matrices that are close to the semi-stable in the
semi-simple. I'm sorry, I'm
semi-simple. Yeah. So I haven't thought about the question from that point of view. So I can just say possibly. I guess so, but for us, so we haven't looked at it from that perspective. So it's just, I mean, this clearly we just classify. So we classify the semi-stable, the stable, the unstable, the polystable elements, and this quotient morphism just exists for abstract reasons. So we didn't think about making.
Do you know any invariant function other than the Pfaffian? I mean, there's probably some functions.
Yeah, there are. I think, yeah, they have been studied, but it's not really necessary to talk about them. So because we always, sorry, I will have to show you this. So here you can see that. Yeah, so here's this list. Hope you can see that. So here's this list of 6 types. Also, it's very dark in here now because there's heavy rain and a thunderstorm. So this is the list of 6 types, yeah, that we get. So what are the players here? So the node up to L4 are independent linear forms on P4, and this Y is the rank 2 locus of the respective matrix M here with scheme structure given by the 4x4 sub-Pfaffians, and S is a syzygy matrix of M, so a matrix with columns representing a minimal system of generators for the kernel of this M. And the last column here gives the stability type. So we were stable, 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 strictly semi-stable, not polystable, not same and polystable. So I mean, it's probably, so this is, yeah, so I don't want you to internalize that table. It's just proof that we've actually done that work. So this is what you get. And yeah, so let me go back to my, sorry, let me just go back to my iPad. So what is happening here? Why can I not? Let me just see. So I want to share. Okay, let's try this. Okay, now it's, no, it's not this, it's this one. Yeah, sorry. So now you can see it again. So these are the 6 types that you find. Okay, so I should also, yeah, maybe I should kind of have momentum, otherwise I don't get to the end of this. So this is M. So now what I want to look at is a different space, M tilde. So now what I look at is the following. So I look at S semi-stable times cubics, space of cubics. And so with this here, with its natural G action, so G acts trivially on the cubics, and it acts in the usual way on this S semi-stable. And sorry?
Is it P4?
It's oh, sorry.
P4.
It's P4. Yeah, it's P4. Cubics on P4. Yeah, sorry, sure. Yeah. And so we have this quotient for this action. Okay, so the quotient. And in here, so in here, we have a G invariant closed subset. So I want to look at the G invariant closed subset, which I want to call as twiggle semi-stable. And so here I want to look at pairs consisting of well, a Skew 6x6 matrix of linear forms on P4, which is semi-stable for this action, and a cubic. And I want that the Pfaffian, the Pfaffian of this matrix, so the 6x6 Pfaffian, yeah, so just the Pfaffian, that is, this Pfaffian should vanish on the cubic defined by F. And I also want that X contains the rank 2 locus with reduced structure of this A1. With its reduced structure. So that turns out to be a G invariant closed subset, and this twiggle or tilde semi-stable then maps to some closed subvariety M tilde in M times space of these cubics. So P4 is closed. So this is some projective variety, comes with a projection onto M. And so this is the projection onto M. In M, we have the locus M naught. These are matrices or classes of matrices with vanishing Pfaffian. With vanishing Pfaffian. And I also want to look at the preimage of this M naught under the projection. call this M naught tilde. Clearly, this projection is, so this is an isomorphism, so over M with M naught removed. So so M tilde with M naught tilde removed is isomorphic via this projection to M with M naught removed. And I can also describe what M naught tilde is. That's this, oops, we have this theorem, which, well, I'll state, not really prove in detail, so this is more like a survey of the results that we got. So this M tilde is irreducible. This M tilde is irreducible, and this M naught now decomposes into two divisors, or rather decomposes in the following way. So it decomposes into one locus A. So both, well, let me start with B. So this is, B is irreducible, is an irreducible closed codimension 1 subvariety. Actually, this is dimension 38. And A is also dimension 38, so this is irreducible locally closed. So it's an irreducible locally closed subvariety. So if you take the closure, then certain points in the closure that are not in A will actually be in B. This is an irreducible locally closed subvariety, also of dimension 38. And yeah, and if you take the closure and this and remove A, then this consists of points of B. So these two intersect, and actually we can describe A and B more explicitly. So where A can be identified with well, the following. So I won't tell you how the isomorphism or how the embedding works, but you can identify A with say pairs C, X, where C is a conic on the cubic X. So this is a closed subvariety in the Hilbert scheme of smooth conics, say in P4, cross cubics. Cross cubics. Right. So this is the space of, yeah, basically this incidence correspondence conic lies on cubic, and B and B can be identified with a space of pairs of lines lying on X, which may coincide. So this is a, yeah.
In the singular.
Sorry, couldn't hear it.
This is where the Pfaffians have run less than 2.
Yes,
C
that's right.
Right.
That's exactly right. Yeah.
So C is contained in the singular locus of X, like the vertex of a cone.
No, C need not be. It's just a conic. It could be a conic on a smooth cubic in general. I mean, the cubic could be smooth, but C is, I mean, I think we talked about that also last time. So we had this, so where was this incidence correspondence? Sorry. So I said that, so what I want is, so, I mean, suppose X, so suppose the, suppose the Pfaffian of M is non-zero, then clearly, I mean, I'm just saying the six, so the Pfaffian of A1 or of M is certainly contained in the ideal of 4x4 sub-Pfaffians of A1, right? Just by Pfaffian Laplace expansion or what. So it's automatic. So X is not singular. If X is there are lots of pairs of smooth cubics and conics lying on them. Or maybe I'm misunderstanding the question.
I think it's okay. Thank you.
I mean, for example, yeah. So I'll say more about that in a second. So I have this M tilde now, right? And M tilde also projects onto the cubics. Right, and for example, I can wonder about what the fiber is over some smooth cubic, or also over singular, possibly even reducible cubics. But I can wonder about what this fiber is, and well, I'll tell you in a second what this space can be identified with. So this can be identified with well, a certain modular space of semistable sheaves on the cubic. So actually, some Druel and Beauville modular space of semistable sheaves, certain Chern classes on the smooth X. So that was studied previously by Beauville, and I'm just saying A and B will then intersect this M tilde also in divisors that were studied previously by Beauville and well, all right, and well, that's a smooth cubic. So I'll say more about that towards the end of the talk. So if I get there, yeah. So maybe let me just, if it's okay, I'll just go on and talk a little bit about matrix factorizations, so that I at least mention matrix factorizations. Yes, but the point is really we can describe this M tilde. Well, we can say something about it. It's irreducible, and we can, yeah, explicitly describe this exceptional locus, this M tilde 0. We don't really know if M tilde is smooth, which is also a question, but we are working on that right now together with Lucas Buhr. So that's also it's probably mildly singular. It's not really smooth, but it's very mildly singular, I think. Okay, now what is the connection? So the connection to matrix factorizations. So this M tilde has another description using matrix factorization, and I'll just tell you about that now. So I want to define a space of matrix factorizations, which I want to call matrix factorizations of intermediate Jacobian type. Maybe that's not a very fortunate name. And it's the following. So yeah, okay, so this will be a subspace now of the product of three projective spaces. So these are projective. So one projective space is the projective space of maps from 201. Everything is on P4 201 plus 6 of 2 to 2 04 plus 6 03 cross. So in this space we have a point which I call A. So typical point in there will be called A. Cross the projective space. Here we have now hom from so this is 201 plus 6 to 201 plus 602 cross again the space of cubics on P4. So the second factor I call a typical point B, and in this last factor, typical point will be called, well, square brackets F. And so what do I mean by that? So A matrix, so A is really the projective point associated to a matrix of forms on P4 where we have well a 2x2 block of cubic forms in the upper left hand corner. Then we have quadratic forms here, 2x6 quadratic, and down here we have a 6x6 matrix of linear forms. And also I want that I want A and B to be skew. Should be skew symmetric matrices, skew 8x8. So A looks like this. A is skew. A is skew. It's 8x8. It has this 2x2 block of cubic forms here in the upper left-hand corner. It has a 2x6 block of quadratic forms on P4 here, A2. Next to it, and then A1 is a skew 6x6 matrix of linear forms, and B looks like this. So there's a skew matrix of constants here, B naught, 2x2. Then we have a matrix of linear forms, again 2x6, and we have a 6x6 matrix, B2 of quadratic forms. And I impose that, so I can do first B then A, and first B then A. And if I do that, so this ought to be a matrix factorization. So I want to get F times the identity, the 8x8 identity matrix, but I only want this. I want this equality up to homothety, yeah? So I want this equality of projective points. And should also be the same as BA. So AB should equal to BA should be F times this 8x8 identity. So AB is a matrix factorization associated with this cubic F. And also I want that the Pfaffian of A should be, so the projective point should be the same as the Pfaffian of B should be F squared. So sorry, so this is a large space, well, large, or it is this space, yeah, so it's a space consisting of triples, yeah. So we have this one matrix A with B, and we have a cubic F. And then there exists a natural action of a non-reductive group, gamma, say, on this space. Well, this is just the automorphism group of, so where is it, this graded free bundle here. Yeah. So this is not reductive. So this has a non-trivial unipotent radical, certainly. So what we can say is the following. So we denote by MF semistable and MF polystable the loci, or just the subsets of MF, where this matrix A1 is semistable or polystable. So we've this matrix A1 here, which is a 6x6 matrix of 6x6 skew matrix of linear forms on P4, and we can, this is semistable or polystable or stable. And so here's the theorem that we can prove. It's a slightly weird theorem, so it's not quite satisfactory yet. So first there's a well-defined map from semi-stable matrix factorizations of intermediate Jacobian type to S tilde semi-stable, which is the obvious map. So you take a triple A, B, and F, and you just map this to A1 F. And so this induces a map from MF polystable. So those matrix factorizations for which this A1 is polystable to M tilde. And the fibers of this latter map are precisely gamma orbits. So the fibers of this map are precisely the gamma orbits. So in this sense, sorry, so this sounds terrible as a theorem, but in this sense, so this is a purely set theoretic assertion, but somehow in this sense, this M tilde should be thought of as the moduli space of matrix factorizations of intermediate Jacobian type, or the quotient somehow of this space of matrix factorizations by the action of the non-reductive group gamma. But we cannot really say that in a satisfactory way yet. So somehow what this Lukas Buhr, this PhD student in Mainz, was looking at was applications of non-reductive GIT, but we somehow can't really subject this to this framework provided by non-reductive GIT. So I cannot really say that this M tilde is in any sense the gamma quotient of, say, MF semi-stable by this group gamma. So I don't know how to say that. I mean, non-reductive GIT, I mean, if anyone is an expert in non-reductive GIT and somehow knows how to do this example from that point of view, we would be very grateful for any hints and suggestions. The different approaches that one can try, I mean, one can first try to divide out the action of the unipotent radical, but the action of this unipotent radical in this case is not free on this MF semi-stable, and also the dimension of the stabilizer jumps.
You should talk to Frances Kerwin.
Yeah.
She knows, she's worked on this for the last 20 years.
Yeah, maybe we should, yeah. Also, Lucas, I think, looked at this work, but we couldn't just couldn't use it. so far we haven't managed to somehow do this example. But I think there is a great arsenal of techniques somehow provided by non-reductive GIT that allow you to construct quotients in a more conceptual way in various setups. But it's not so clear which setup this example can be subjected to somehow. That's the problem. All right. So now I only have 5 minutes or so left. So then maybe what I should tell you, so maybe what I should tell you is what the connection to the intermediate Jacobian is really in this case. What is the connection of M tilde or of the fibers of M tilde over cubics to intermediate Jacobians? So as I said, so for X smooth, we can look at the pre-image here of the smooth cubic X under this map from M tilde to the space of cubic. So we just look at all pairs here, M, comma F in the space M tilde, for which X is 0 locus of F. And so that's just a subset of M tilde. And so what is it? All right, so what is it? So what you can do, so you can consider this Maruyama or Druel moduli space. Which I'll call mx bar of equivalence classes of semistable sheaves on the smooth cubic X with Chern classes C1 equals 0, C2 equals 2, C3 equals 0. So that's a compactification. That's a compactification of the space of stable vector bundles. Stable vector bundles of rank 2 on X with C1 equals 0, C2 equals 2. And Beauville has studied this. And Beauville shows that this space, this is isomorphic to the intermediate Jacobian of X blown up in the Fano surface of lines. Blown up in the Fano surface of lines in some surface. Okay, so now so what I want to, so what we prove is this. So this is really just what we are looking at here. So this is just this M tilde X. So we have an isomorphism, exists an isomorphism between this mx tilde and this Druel Maruyama Beauville compactification of this space of stable vector bundles of rank 2 and X with these Chern clouds. well, we have such an isomorphism, and this is, I want to call this kernel of adjoint, because the way this isomorphism works is you just take your matrix M. So what you take is your matrix M, and you have a pair here in M tilde X, so consisting of this matrix M and a cubic. And suppose this is polystable. And what you can then do, you can take its adjoint and look at it as a map from 6OX of -1 to 6OX of 1. This is quadratic entries here. This is the Pfaffian adjoint. And the kernel, so this Fm, so you look at it on X, on the cubic X. And the kernel, this Fm, is the thing you're mapping this to. So you're mapping this to Fm, to the class of Fm. So that's what you're doing. Right, so there is this isomorphism. So in some sense, what you should, so how you should think about our construction is that somehow we have, we found a way to associate also to, well, very badly singular cubics, especially also reducible cubics, X, an analog of this Maruyama-Druel moduli space, which is just, well, some controlled birational modification of the intermediate Jacobian of X. Yeah, so because we have our M tilde, globally over the space of cubics, we can also talk about fibers here, M tilde X over reducible cubics X of very badly singular cubics X. And especially this allows us to construct degenerations of these kind of intermediate Jacobians blown up as Fano surfaces of lines, or degenerations of these moduli spaces of semistable sheaves on smooth X to some interesting other varieties. And so that is what we are trying to. So that's how far we've got. So maybe I'll finish here. So this allows us to construct interesting decisions. Of course, lots of other questions then can be asked. For example, if you have a singular cubic, say X, the union of singular cubic threefold, maybe even reducible. Yeah. So for example, if X is the union of a quadric and a linear space, what does the fiber look like? What is this M tilde X in that case? We don't know yet, but that's what we're working on at the moment. Yeah, so maybe I should stop here.
Thank you very much. Questions, comments, answers? Maybe some answers to some questions. I guess I just have something that I'm always curious about in these situations is it easier if you degenerate to a hyperplane and a conic, or is it easier if you degenerate to like free hyperplanes, like this M? What's the fiber? Is the fiber easier in one case versus the other, or?
I don't. I mean, in the case, I mean, the point is that, I mean, maybe just because also we don't have the technical prerequisites to deal with this properly, we eventually always want to look at strictly semi-stable degenerations. Yeah. so semi-stable degenerations, but with smooth total space. And to pass to that setup and to singularize the total spaces of the possibly initially the possibly initially singular total spaces of degenerations, that's more difficult, I think, in the case where you degenerate to 3 hyperplanes. But we don't know. I mean, both are interesting, yeah. So I cannot tell you which one will be more promising. Of course, you can degenerate. Yeah, you can degenerate to a 3-dimensional quadric in the hyperplane, and before you could degenerate to 3 hyperplanes. Sure.
So basically, so the hope is you find some interesting degeneration, which will be correspond to a degeneration of the cubic, right? And then on that space, you want to, like on the m tilde x, you want to investigate the existence of like these algebraic classes.
Yes.
Yeah. Great, thank you. Further questions? There's a natural question, which is that if you look at mirror symmetry, somehow these categories of matrix factorization have some meaning in there, and I don't know, is there like a, I don't know how to formulate this. Maybe Tyler knows. I'm actually repeating a question by Tyler, so I was just hoping he would like save me, while I start stumbling. So
is there a connection to mirror symmetry? No, I don't know. I mean, the matrix factorizations just give us a way to very concretely describe this m tilde, or get an alternative description of, in this case, of m tilde. So there is no. Right. So I mean, the question, I think, what is interesting about this, I mean, lots of people are interested, I think, in constructing moduli spaces of matrix factorizations in different contexts. And at least Manfred Lehn and people like that have so far apparently always run into certain stumbling blocks in applying methods of non-reductive GIT in that endeavor. And so what's interesting somehow is that at least in our case, we kind of know what the quotient should be. In this case, it should be m tilde. So if we divide by our non-reductive group gamma, if we take our space of matrix factorizations, divide by gamma, and somehow the good quotient of MF semi-stable, I think, should be m tilde. But so at least we know the answer to the question. But somehow it would be nice to somehow reconcile that with this framework of non-reductive GIT. Certainly, you can describe an open subset of m tilde by methods of non-reductive GIT, where you just remove m no tilde, right? But this is not what you want. This is not really what you want to cast out your net as far as possible, and you actually want a compact m tilde in the end. So there is.
Maybe I can try to articulate Michelle's question in a different way. So like, if you start with the derived category of the cubic threefold that you have, then there's an admissible subcategory that's given by the category of matrix factorizations with respect to your polynomial f, but defining the zero locus.
Mm-hmm.
So then, can you say anything about the category of matrix factorizations from this incidence variety that you're creating? Because it seems that like the fibers are all elements that are objects in your matrix factorization category, but they have like a fixed dimension. So
yes,
do these generate? Like, I mean, there should be some type of exception. Well, it might be exceptional. Do you know, can you say anything about what the structure of that category would be from?
No. No.
Okay.
It would be interesting. It's certainly an interesting suggestion, but we haven't pursued it, and no, we haven't thought about it at all. Well, it sounds interesting, but we haven't thought about it in that way at all.
Okay, thank you.
And that's why you talk to people who do mirror symmetry. They can give you ideas.
Yeah, sure.
More questions? More questions? Wait.
So we've all got knowing this tonic bundle and Prim construction of the intermediate Jacobian. But I mean, one of the things that you're analysing here is how it depends on the choice of a line. So
But I can't hear you. So take this conic model initially. You're choosing a line, yes.
there's a two-dimensional family of lines. Each of those gives you a conic bundle.
Yes.
So it might be interesting to know, is there a way of constructing the intermediate Jacobian not using projection from a line? Using some bigger family of curves, and their arbolias will be matrices.
But with a goal of doing what?
I don't know. I mean, you're studying, complicated ways of presenting the variety in the hope of seeing better degeneration.
Yes. You mean maybe it would be possible to find a different description of the intermediate Jacobian altogether? Maybe not. I mean, this description and as a Prim variety is somehow convenient for us, because eventually we want to know if there is a class, if somehow half of the class of this Prim curve can be represented by an algebraic cycle. Yes, so that this minimal cohomology class. So this is somehow what we're interested in. So this,
but that's the theta divisor.
Theta to the 4. It's a curve, so it's this minimal class theta to the 4
If you
divided.
know the theta, then you know that class. You don't need to know it's a Prim.
No, that's true. There could be a different description that's even more convenient. I agree. But we couldn't think of any other. But so we just.
So to go back to the question you started with, do we know any case in which this retract rational question has been answered, either positively or negatively?
No. I mean, this class is algebraic. So Voisin shows that this class theta to the 4 divided by 4 factorial is actually algebraic on a countable union of closed subvarieties of codimension less than or equal to 3. I think that's what she proves. So it does happen sometimes that this class is algebraic. But the question is, the question is what happens for general X? Yes. So there are some special cubics that are Chow zero. So there are then some special cubic threefolds, right, that are Chow zero universally trivial, but that also doesn't say that they are retract rational or stably rational. Yeah, because being Chow zero universally trivial is weaker. But it's still very plausible that, for example, could be that a general or a very general smooth cubic threefold is not Chow zero universally trivial, and hence in particular not retract rational and not stably rational. No, there is no stably rational smooth cubic threefold known. No retract rational one. No.
Great, thank you for that. Are there more questions or comments or answers or? So maybe there are no more questions. So Christian, thank you very much for giving this beautiful talk. Oh, wait, there's a question. Okay, so there was a hand wave by Miles. Yeah. Okay. Wonderful. Thank you so much for joining us today, and happy Easter, I guess. And
yeah, happy Easter to everyone.
Yeah. Cheers. All the best. Bye bye. Go to direction. This way, this way, this way.